All right, we're live. Hello, everyone. I'm Will, and welcome to the first of a new set of Hangouts on Introduction to miniKanren and the technologies that you need to be familiar with to understand miniKanren and the interpreters written as relations, and Barlaman, which is this tool that can do program synthesis based on relational interpreters and so forth. So if that's of interest to you, you're in the right place. We're going to have these Hangout series on Saturdays at, I guess, noon Pacific time, 3 p.m. Eastern time in the US. And if you're interested, you can join the miniKanren mailing of the Google groups for miniKanren or for Barlaman Editor or the miniKanren Hangout series. We'll announce the Hangouts there. We've got a full house today. And basically, the idea here is to try to introduce the core ideas necessary to understand what's going on with miniKanren or relational programming. So if you want to learn about logic programming, if you want to learn about miniKanren, if you're curious about interpreters or how you might write a non-trivial program as a relation in the style, you want to know how Barlaman works under the hood, those are all good reasons to be part of a Hangout. Also, we're going to talk about some ideas leading up to miniKanren and all that are also just interesting, like scheme programming, introduction to scheme, recursive Lisp programming, stuff like that, symbolic programming, and also things like how to write an interpreter, a Lisp interpreter written in Lisp, that sort of thing, metacircular interpreters, and continuation passing style and other program transformations that are related to that. So hopefully there'll be an interesting series of topics that lead up to miniKanren. The last Hangout series we did was about 40 hours, but that was also a mixture of introductory materials and much more advanced hacking on miniKanren. So this series, I think, is going to be more directed and hopefully will be so much shorter in terms of getting up to things like the relational interpreters. We're also doing Hangout series on Sundays at the same time, which is going to be more of an advanced miniKanren, Barlaman, free-for-all, and we can talk about more advanced topics related to relational programming. Okay, so without further ado, I think let's talk about scheme a little bit, which is the language we're going to be using. So miniKanren, which is the logic programming language that we're trying to get to and describe how that works, was originally written in Scheme, and it's basically an extension of the Scheme language. And the reason it was written is that I was writing a book with Dan Friedman and Oleg Kislyak called The Reason Schemer, and we wanted to have an implementation of logic programming for our book based on work that Dan had been doing and Oleg had been doing on logic programming when I first started at grad school. And so this book, The Reason Schemer, is a continuation of a series of books on Scheme and Lisp that Dan has been writing for many years. The first is called The Little Schemer. So Scheme was the language we picked, and at the time at Indiana University, Scheme was the language that was used. So this was sort of the English of Indiana University was to write stuff in Scheme. Everyone knew Scheme. But since then, miniKanren has been ported to many other host languages. So Clojure is probably the most popular. Racket, which is a Scheme-like language. I'll talk a little bit about the difference between Scheme and Racket. It's also been ported to Haskell. In fact, sort of the first modern implementation of miniKanren, if you will, was written in Haskell. And now there are versions in all sorts of languages, Ruby and Python, and finally Java, and so forth. So I think there are at least 50, there are probably between 50 and 100 implementations of miniKanren now in various languages. So anyone who wants to learn logic programming in this style tends to implement their own version of miniKanren, or there's a simplified version called microKanren that people will implement. And microKanren is under 50 lines of Scheme code, so it's very, very short. So you can understand the core ideas very succinctly. And I think that's something that's true of all of these core ideas, that they're very simple in a sense, or they're very elementary or very small, but they're very deep. So for example, the interpreter, the scheme interpreter written in Scheme, you can write that down on a 3x5 card or 4x6 card. And so it's very, very small. That's 4 inches by 6 inches for anyone not in the United States. It's like this big or something. It's small. I don't know what that is in metric, but anyway, so you can write this down on a tiny little index card and fit all those ideas there. So that's one of the themes we're going to have, is that we're going to be trying to look at systems that in some sense are very small. They have very few moving pieces, but they're very deep. So miniKanren only has basically 3 core operators. Scheme only has, the scheme is based on something called Lambda calculus. That only really has 3 parts. So, we're talking about systems where they have like 3 moving parts, and you can extend it, but the 3 moving parts are sort of the essence. And so we're going to see several systems that have about 3 moving parts each, and yet you could spend your entire life studying them, and people have. So I think that's sort of the richness of something like chess or Go. You can have very simple rules, but the implications are extremely deep. So that's I think part of the appeal of these ideas. You can keep going deeper. All right. So one question is, what are the 3 operators in miniKanren? Unification, conjunction, disjunction, fresh. That's 4. Yeah, so it depends how you break it up. So miniKanren, if you're familiar with miniKanren, you basically have equal, which performs something called unification. You've got fresh, which introduces new logic variables and does conjunction. And then you have condi, which allows you to do disjunction. So those are really the 3. You could also break it down differently, like in microKanren, where you have unification, conjunction, disjunction. And the introduction of fresh variables, you could say that's the 4th one, yeah. So maybe it's 4 operators, depending how you look at it. But the point is, you have a very, very small language. You could also kind of break up Lambda calculus maybe into more pieces. Also, you could say, well, capture avoiding substitution is really this complicated operation, and but in any case, you have very, very small core languages. If you compare that to a language like C++, right, that's an enormously complicated language, or Ada or PL1 or something like that. If you're familiar with these languages, they're gargantuan. So these are very minimalist systems. You can extend them, but the core ideas are very, very tiny. Okay, so one question before we get started is, well, what is Scheme, or what's the difference between Scheme and Racket, or Scheme and Closure, or Scheme and Common Lisp, or what is Lisp, or so forth. And hopefully we'll get a better sense of what Lisp is. But basically, I would say Lisp is a family of programming languages. It's quite old. It started basically in the late 50s, invented by John McCarthy. And it was inspired by something called Lambda calculus, which is a logical formalism created by Alonzo Church in the 1930s. And Lisp is a sort of very sparse notation for representing a version of the Lambda calculus. And so it's got sort of very nice mathematical properties, and very deep and in some ways subtle in terms of all the implications. But it turns out that programming in Lisp feels very different than programming a language like Java. It has a different set of core concepts, although languages like Java are adopting more ideas. So for example, Lambda in Java 8 is taken directly from the Lambda calculus and Lisp and so forth. So some of the ideas from Lisp have percolated into other systems, like the ideas like garbage collection. That's now become sort of ubiquitous for a new generation of languages, except for Rust maybe. There's this big family of languages called Lisp that's been around since the late 50s. And Lisp is known for being based on Lambda calculus. It's also known normally for having what's called a parenthesized notation based on something called S expressions or symbolic expressions, and we'll see what those are. So you tend to see lots of parentheses in Scheme code, and that maybe freaks some people out or scares them or turns them off. But it turns out the parentheses have some really great advantages, and there's a reason that Lisp programmers haven't really wanted to give them up. So we'll learn about that. We'll learn about functional programming and how Lisp can be used for functional programming, where you write your programs as functions, mathematical functions, and what that might mean. it turns out there are many versions of Lisp because Lisp is such an old language. There have been countless varieties of them. And if you're interested in the history of Lisp, there are lots of resources. There's a great series of books called The History of Programming Languages from the ACM. So Hopple 1, Hopple 2, Hopple 3. And you can find these articles in the Hopple conferences about the history of Lisp and talking about all the different varieties of Lisp and so forth. Guy Steele and Dick Gabriel have a famous talk about all the various families of Lisp, for example. But the most, I should be careful with the word common because there's a Lisp called Common Lisp. Probably the Lisps you're most likely to encounter today are Common Lisp, Scheme, Racket, Closure, maybe Emacs Lisp if you do Emacs. There are also an AutoCAD, there's AutoLisp and things like that. But I would say the most common Lisp-like languages that are in general use for general programming would be Closure, Scheme, Racket, and Common Lisp. But they're always, there are new Lisps being created all the time, like Logo in some sense is like a Lisp. So, Scheme came out in 1975, and that was created by Guy Steele and Jerry Sussman. Jerry Sussman is well known for co-authoring a book called The Structure and Interpretation of Computer Programs, or SICP, or SICP. And that book is fantastic, and it's available for free on the MIT Press website. And the videos from SICP are also available online. That's something that got me involved in Lisp, and it's a very beautiful set of ideas about computer science and computation that you can find in SICP. So this was the classic introductory book used at MIT for several decades for their intro class. And so it's just a lot of people consider this the best computer science textbook ever written. I will not say whether or not I think it is or not, but it's certainly fantastic, and it's full of ideas. And I have a PhD in programming languages. I could still pick up that book and learn lots of things from going through it. Just very, very deep. And that book is written using Scheme as a notation. So Scheme came out in 1975, and it has a very interesting history that I could get into, and I kind of won't get into it because if you want to know about that, I can point you to all sorts of resources that tell you about it, or we can talk about it later. But anyway, that is a Lisp that has been under development since 1975, and it has, in some ways, fixed a lot of problems with earlier versions of Lisp, having to do with the scoping of variables and things like that. And now, more recently, starting in the 1990s, really, it got a very powerful macro system. So that's another thing that Lisp languages tend to have, is something called a macro system. And macro is an overloaded term because it can mean all sorts of things. But in this sense, it means that you can write some code in Scheme that will generate Scheme code in a very sophisticated way. So there are other types of languages that support macros, like in the C programming language, there are macros. The C macro system is very low level compared to the Scheme macro system. And the Scheme macro system has a whole bunch of guarantees, and it's designed in a certain way to avoid classic problems you can get into when writing macros. And so it has a very sophisticated macro system. And one of the advantages of having a macro system like this, and other Lisps share this, is that you no longer have a fixed programming language. You can extend the language. So people say that Lisp is a programmable programming language, is one common saying. And so you can extend Lisp pretty easily to do other things. And that's exactly what we do with miniKanren. We take Scheme and we add some macros, and we add some functions, and then we end up basically with an extended Scheme that would be like if the designers of Scheme had also decided to add logic programming as a fundamental aspect of Scheme. So Scheme is still under development. The latest version of Scheme being developed is the latest standard is called the R7 RS standard. There's R6 RS before that. There's R5 RS, which is sort of sort of the classic scheme that's been around since the 90s. And we're going to use basically a subset of scheme that's very small. It's called, basically R5RS scheme or something equivalent. So this is a scheme, subparts of scheme that are very common to other systems. There's another language that started out as a scheme. It was called Doctor Scheme. And that branched off to become another language called Racket, which now has a very fancy macro system and supports all sorts of other languages besides scheme-like languages. And so now, the most sophisticated macro system is available in Racket. Well, what we're going to do is simple enough. We're going to use a simple enough subset of scheme that the code will run in scheme or run in Racket, whatever. Should basically not have too much difficulty going between them. If you wanted to use another Lisp like Clojure, it turns out that it's pretty easy to translate most, if not everything we're doing into Clojure. Syntactically, it'll look a little bit different, but if you know Clojure, you probably shouldn't have too much difficulty. And if you know Common Lisp, a lot of the things also should not be difficult to translate. And there are implementations of miniKanren in all these languages. As far as, I could get into the whole history of Racket and how that kind of went a different way, but I would say to answer this question, what's the difference between Racket and Scheme? I would say that many of the Racket people have described Racket as a batteries included scheme. So Scheme historically has been sort of a minimalist language, has very few things specified in language. So in R5RS Scheme, there was no exception mechanism specified. There really was almost nothing about even an error mechanism specified. The macro system wasn't specified in any real detail, on and on and on. The input-output functions were not described in much detail. The R6RS has more detail, and R7RS has more detail. But the idea of Scheme was to have like this very small language that's very simple, is easily extensible, and could easily be taught to people, and could be hacked to do experimental work in programming language research. Racket is, sort of its origins was as a scheme with a lot of features added to it. Okay, so batteries included scheme, and over time it sort of acquired this more and more powerful macro system. And so now one of the cool things about Racket is that Racket's really a bunch of languages layered on top of each other using this macro system, where you could extend this very small core language with a higher level language, and then build a higher level language on top of that, and so forth. So the current Racket implementation, has I think several dozen languages inside of it built using this macro extension mechanism. So it's very powerful. What we're going to be doing is going to be more minimalistic and sort of more in the mindset of traditional scheme, and trying to keep everything small, the ideas small, and the number of operators small. But if you want to do programming in large, then having all these extra features like in Racket or in Clojure is a helpful thing. But since we're mostly interested in pedagogy right now, we're going to try to keep the number of features small. But the bottom line is, you could use Racket, you could use Scheme. You should be able to run this code with either no modification or with small modifications. If you run into trouble, let me know, drop me a line. Okay. Argument evaluation order, yes. Daniel points out that there are some semantic differences. So in Scheme is deliberately underspecified in some areas. So when you make a function call, the order in which the expressions within that function call get evaluated is unspecified in Scheme, whereas in Racket they are specified. They're evaluated left to right like they are in many other languages. So there are some small semantic differences in that. The way quotation works is a little bit different, things like that. So you might see that you'll get slightly different behavior in some cases, but I think we're going to stick to a subset of Scheme that is basically going to work the same in both. So if there's anything that really is different, we'll try to keep an eye out for that. Okay. All right. Any questions before we continue? Okay. If you have any questions, feel free to type it in. All right, so let's learn some scheme. Let's learn a little bit of scheme and get some code going. Let me do some screen sharing. Ah, here we go. Well, it's been too long since I've done a Hangout on air because I'm stumbling around for the keys. Okay, great. Hopefully you can see that. I'll make the font a little bit bigger. All right, so I'm going to use the programming environment that I tend to use for real, which is the Emacs text editor. Doesn't really matter which text editor you use as long as you're not using a word processor like Microsoft Word, but that's going to do some formatting you don't want. But any text editor will work. You could use Dr. Racket. You know, if you just download Racket and use the Dr. Racket editor, you can use that just as well. So I am going to, let's see, I create like a new directory. So, okay. All right. The first thing I'll point out is I create a file called hangout1.scm. So scm is a standard extension for Scheme. You can also see ss as an extension of Scheme. If you're using Racket, you might use .rkt as an extension. Okay. So let me bring up my Emacs a little bit. Does that help with the blocking of the portraits or not, Sean? How's that? Is that better? Okay. Just want to make sure that everyone can see everything. Okay, so what I'm going to do is start up a version of Scheme called Shea Scheme. And Shea Scheme is my preferred implementation of Scheme. I've been using it a long time. And the nice thing is that it's now been released by Cisco as an open source project. You can download it. For a long time, it wasn't available as an open source implementation, but now you can download it. And the other interesting thing is that Racket may be rebuilt on top of Shea Scheme. So, maybe there will be sort of a coalescing to some extent of these technologies. I think Racket would still be much more battery included, but Shea Scheme also includes various extensions and libraries that are useful. But anyway, so Shea Scheme is the implementation I tend to use. There are many implementations of Scheme. In fact, my friend Aziz said that Scheme was probably the most implemented programming language in history because anyone who really gets into Scheme will probably write at least some little Scheme compiler or something like that. So there are countless implementations, but there's still even probably a dozen or 2 dozen implementations that are actively maintained, and you might download and something like that. There are lots of implementations, but Shea's the version I'm going to use. Probably shouldn't matter. You should be able to use Guile or Gambit Scheme or Vicari or let's see, Larceny. There's a whole bunch of schemes out there. It doesn't really matter which one you're going to use, whichever one you're comfortable with is fine. So when you start up Scheme, you're going to see that there's some sort of prompt or evaluation loop. This is called the REPL. The REPL. That's the eval. We're going to, or the REPL will read an expression in Scheme, evaluate it to tell you the value, and then print out the output. And it does this in a loop over and over again. So if I refer to the REPL, that's what I'm talking about. It's this interactive environment in Scheme that we can type things in and see what they evaluate to. And if you're familiar with Ruby or Python or a language like that, this should not be a new idea. Okay. So we've got the REPL, and we can write our first Scheme program. So I'm going to write 5, and I hit return, and I get back 5. So 5 in Scheme evaluates to 5. We can also do 6. 6 evaluates to 6. And also evaluates to itself as well. So this is one nice thing about Scheme implementations is that Scheme handles what are called arbitrarily large numbers or big nums. So we can do arithmetic and have really large numbers and not have a problem there. Of course, there is an efficiency trade-off in the implementation, but it's a nice level of abstraction, not having to worry about having some really big number give us an overflow error or something like that. Okay, so that's the simplest programs we can write, or something like 5. They just evaluate to themselves. There's a self-evaluating value. And we can also try to do something simple like add 2 numbers. So we could add like 3 and 4. Now, if I were writing this in another language, I might write something like 3 plus 4, or 3 plus 4 and a semicolon, or something like that. If I write 3 plus 4, I get this kind of strange looking output. I get a 3, and then I see this hash procedure plus and a 4. So what's happening is I'm actually seeing the output of 3 different things. So Scheme doesn't consider this an addition expression. Scheme says, oh, you're entering 3 different values, and I'll just print those out for you, the values. And it turns out the value of plus is a procedure. That's also bound to the addition arithmetic. So what we're seeing is 3 evaluating to 3, this plus identifier evaluating to the procedure that does addition, and 4 evaluating to 4. So syntactically, we didn't write the expression down correctly for Scheme to understand we want to do an addition. So the way we do addition in Scheme is similar to the way addition was done on old HP calculators. In old HP calculators, if you wanted to add 3 and 4, you would do 3, 4, and then plus at the end. So you would sort of push onto a stack or a sort of list of values that you cared about the numbers, and then you'd tell the operator, and then the operator would consume whichever numbers were at the top of the stack and manipulate those. So we'd say, oh, okay, well, plus takes two numbers, and the last 2 numbers were 4 and 3, so I'll add those and give you 7. Okay, so that's the idea of postfix notation or RPN notation. So Scheme and Lisp work similarly, except we put the operator at the front instead of at the end. So we're going to have plus, and then plus is going to consume some number of arguments, like 3 and 4, and then add them together. But we want to make clear what's going to happen. We want to make it unambiguous, because maybe we have multiple pluses and we want to do 2 additions. Now it's not really clear, are we adding 3 and 4 first, or are we adding 3, 4, and 5 first? And for plus it doesn't matter, but if we add a multiplication, then it does matter which numbers we consume for plus and which ones we consume for multiplication. So this is an ambiguous expression. So we need some way to express which numbers are going to be fed to plus. And the way we do that in Scheme is with parentheses. The parentheses represent a function call. So we're calling the plus or the addition function, and we're saying, all right, call plus on 3 and 4, and whatever value that gives us back, 7, that is something that will then be fed into our multiplication function. Okay, so the way to read is that we're going to add 3 and 4, whatever result we get back here, 7, that is going to get involved in this multiplication. We're multiplying 7 by 5 by 6. Okay, so I can break this down into parts. Let's go back to our 3, 4. And so 3 plus 4 is 7. Okay, and if I were to replace the plus 3, 4 with 7, see that we get 210. So sure enough, that's the way it works. Okay, so this is our first exposure to these parentheses. And if you're used to traditional way of doing arithmetic, then this might look very odd and look kind of awkward. And you can argue whether or not it's awkward for arithmetic, but it turns out to be very useful for other types of programming tasks. And even for arithmetic, there are some significant advantages. So, even though it may not be as readable if you're not used to it, there are some advantages. So, for example, if I wanted to add 3, 4, 5, or 6, and 7, 8, number of arguments without having to, use multiple uses of plus or something like that. So if plus only took 2 arguments, then I'd have to do stuff like this. So this prefix notation allows me to give it any number of arguments. In fact, I could even give it 1 argument, back 3, or I could give it no arguments, which gives me back 0, which is the additive identity. It's the number that if you add to a number, doesn't change it. And similarly for multiplication. So I could multiply a whole bunch of numbers times the star operator. And I could also multiply just by itself, or times 1, I mean, not by itself. Or multiply 0 numbers, give me back 1, which is the multiplicative identity. So just if you multiply any number by 1, you get back that number. Okay, so that's an advantage of this notation. The other big advantage for arithmetic is that you have to write down your expressions in a way where it's completely unambiguous what's happening. So we're just used to, because we were used to math, writing things like that. Okay, but now you have to think, well, which operators come first, and okay, which ones has higher precedence? Well, multiplication has a higher precedence, so this is really the same as if we had written parens around it. So traditional mathematical notation has some ambiguity that you have to fill in by knowing things like the precedence of operators and things like that. And that's fine as long as you really know that convention, but this is something that people can make a mistake in a complicated formula and get it wrong. So by being explicit, we avoid those sorts of issues at least. Okay, so we're always going to be explicit, and we're going to write these parentheses. And what the parentheses are really telling scheme has nothing to do with arithmetic. What these parentheses are saying is that this is a function call. We're calling some sort of function, which in this case is this addition function, and we're giving it operators, which are 3 and 4, or operands 3 and 4. So that's the basic idea of the parentheses. All right, so I will show you, that's also really neat, and this is maybe getting a little ahead of ourselves, but I feel like this is another reason you should understand why we have parentheses. One of the nice advantages about the schemely notation is that we can put this quote character, this tick character, in front of an expression like +3, 4. And now if I hit return, instead of getting back 7, I get back the original expression. So what I've done is I've taken an expression and I've quoted it, and now I get back a list, a scheme list, and this list represents the code, the original code I had. And now I can take that list apart. I can put together a new list that represents code, and then I can call a function called eval. Evaluate. Remember that read eval print loop part. This is the eval part of the read eval print loop. So eval can take one of these quoted expressions that represents, a list basically representing code, and evaluate it. So the thing here is that I can just take this addition expression and evaluate it into my REPL, but I can quote it. And now I get back code, a list representing code. And now I can evaluate that code. And now I actually perform the the function of that code. So I'm adding 3 and 4 to get back the value. So you can play these games where I'm moving between expressions that are going to be immediately evaluated to lists representing code that I might want to manipulate or delay the evaluation. And then I can go back and evaluate that list anytime I want. And in fact, we are going to write our own version of eval. We're going to write an interpreter for scheme that implements eval. And we'll see how that works. And it's very powerful. So we'll implement scheme inside of scheme, what's called a meta-circular interpreter. But that's one of the reasons that this syntax is so powerful in scheme, is that we can just put a quote in front of one of these lists, or one of these expressions, I should say, and that will give us back a list that we can manipulate. So by always having the operator come first in the list, it gives us a regularity of the syntax that makes it easy to do manipulations of the programs. And Scheme also has this very powerful macro system. Racket has even a more sophisticated macro system that allows us to manipulate code in another way. So Scheme is very good at what's called metaprogramming, allowing us to write programs that manipulate or generate other programs. And this is one reason that the schemers really like this, or Lisp in general is very good at metaprogramming. So we'll see more about that. So basically this is an apology, if you will, for the parentheses and the syntax. If you want to think that there's a reason for it, but I know it looks weird to people who aren't coming from a Lispy background. Just I'm just going to say that there are very, very good reasons that Lisp has the syntax, extremely powerful reasons. It is a little unusual. Once you use it and see how it can be used, I think it's maybe worth being a little unusual. Okay, so we've seen how to write a simple call to a function, +3, 4. Now let's look at, let's look at lists. Okay. So we already saw a list. We saw a list when quoted +3, 4. We get a list that's of length 3. The first item in the list is the symbol plus. The second item in the list is the number 3. And the third item in the list is the number 4. So I can grab, well, actually, let me just show you something first. So I can ask a question in Scheme by calling this function called list ? Or list huh, is how a Racker might pronounce it. So I can ask, is the value of quote +3, 4, is that a list? It's like #t. Okay, #t is Scheme's representation of true. So it says true, yes, quote +3, 4 evaluates to a list. I can ask this question also of like 5. Is 5 a list? #f, that's false. No, 5 is not a list. Okay, so one operator on lists is list ? We can also ask, if we have a list, we can ask the length of the list. Ask, what is the length of quote +3, 4? 3. Has 3 elements, plus 3 and 4. Okay, so we can ask the length of the list also. We can also get the first element of a list. And here, once again, sort of like the parentheses, the notation might throw you for a little bit of a loop. And then, not every Lisp uses car and coulter anymore, but there are 2 traditional operators for operating with lists or something else called a pair that we'll see. And in Scheme, they're called car and coulter. You might see these called first and rest in other languages or other similar terms. But the point is that car will give us the first item in the list back. So this is the same as first. So sure enough, we get back the first item in that list, which is plus. We can also ask for the rest of the list, which is coulter. This is rest, and we get list 3, 4. Okay, so you could ask, why in the world does Scheme use car and coulter? Aren't those terrible ideas? Aren't those terrible names? And these are sort of a historical accident which turned out to be a happy accident, sort of like a Bob Ross happy accident. So car and cdr, their original names have to do with very old hardware that early versions of Lisp ran on. And so this has to do with the contents of the address part of the register and the decrement part of the register and all this stuff. So that's where those names come from. But the reason that schemers use those names still is that you'll notice that the C part is the same in car and cdr, and the R part is the same in car and cdr. The only thing that changes is the middle, the A and the D. So you can actually chain these things. So you can write things like is the same as car of some value. Okay, so that's once again a justification for the naming convention, which is admittedly a little strange. If you're unhappy with this, you can redefine car to be first and redefine cdr to be, or you can define something called first, which is car, and you can define something called rest, which is cdr, or whatever, if that makes you happy. But I think it's worth getting used to just car and cdr. So there are a couple of things that are a little odd when reading the code. I guess my recommendation is, just play around with it a little bit until you internalize the meanings. And once you do, then I think it's going to be okay reading it. So the car gives us the first thing in the list. Cdr gives us the rest of the list. And if I wanted to, I could ask for another cdr. So the cdr of the original list gave us the list 3, 4. I can ask for the cdr of that list, which will give us 4, list 4. And I could ask for the car of that, which will give us 4, which is the first thing in the list 4. So I could also I could kind of put these together. I had a car and a cdr and a cdr. So I can just merge the middle letters. So we had an A for car, a D for cdr, and a D for cdr. So that's the same as editor, and that gives us 4. It has the same behavior. So that chaining is why Lispers tend to like these names, car and cdr. There are other ways you can access the list using pattern matching, which we'll see later. And maybe that's a little easier to see what happens. But car and cdr really are the fundamental operations. And if I wanted to keep going down, I could actually take the cdr of the cdr of the cdr of plus 3, 4, and that would actually give me the empty list. So I can cdr down the list until there's nothing left. So I started out cdring plus 3, 4, give me the list 3, 4, take another cdr, gives me list 4, take another cdr, and I get the empty list. Okay, and I'm not allowed to take the cdr of the empty list. That's an error, and I can't take the car of the empty list either. That's an error. Not every Lisp makes it an error to take the cdr of the empty list, by the way. And some Lisps have something called nil instead of the empty list. So Lisps do differ a little bit, but in Scheme you have the empty list. And you're not allowed to take the car or the cdr of the empty list. Another operation, which we have in addition to car and cdr, is called null. Null, tell if an object is or value is the empty list. Okay, so yes, the empty list is the empty list. The list containing pizza is not the empty list. That list is not empty. So we have null. And the other operation that we really care about when dealing with lists is called cons. So cons is short for constructor. It allows us to construct new lists. Okay, so cons is a constructor. And I can make a call to cons. Cons is a function. I can cons, let's say, quote, pizza onto the empty list. Okay, and that gives me the list containing pizza. So you notice I put a quote in front of pizza because I could have said 5, let's say, and that's fine. But if I just say pizza without a quote in front of it, what happens is Scheme thinks that pizza is a variable name, and it tries looking up the value of the variable. So this variable pizza is not bound. Okay, so I could define pizza and give it a name, or give it a value, But if I don't, then pizza will be considered a variable that's not bound, and I get an error. So I can put a quote in front of it, and like we saw before, so quote of pizza, what does that evaluate to? Quote of pizza is pizza. Quote of the list plus 3, 4 is plus. Quote of foo is foo. So the idea is that quote of anything is that thing. So quote of thing gives you back the thing itself without the quote. So if we want to deal with symbolic data, like lists containing food, then I can put a quote in front of these characters, and Scheme will treat that as what's called a symbol. So symbolic data, symbolic value. So I can create a list containing pizza. I can also create a list containing Con's salad onto Con's pizza onto the empty list, and now I have a list containing salad and pizza. So the Con's allows me to add something onto the front of the list. We're going to Con's onto the front of the list. So I can just add another. I don't know, what else is food? How about ice cream? How about milkshake? Ooh, milkshake's good. All right. Now I've got a list of 3 things. So Con's allows me to build up a new list, to add something to the front of it. If you notice, I started out by consing the pizza onto the empty list, quote empty list. Okay. Cons, though, is actually more general than this. So cons can take anything, any value as the second argument. It doesn't have to be a list, actually. So I could say I could cons 3 onto 4, and what I'll get back is what's called a pair, a cons pair. And so the secret is that in Lisp, or in Scheme, there actually are no pairs. There are no lists. There are only pairs. Okay, so cons actually is building up new pairs, and it turns out that pairs that certain types of pairs will appear to be lists. So like list milkshake, salad, pizza, that actually has a whole bunch of, that's made up of a whole bunch of pairs with these dots. It's just that Scheme won't print out the dots because there's a certain structure to this list that makes it easier to read without the dots. So we suppress the dots when we print out the answer. So let's see, if we wanted to look at milkshake, salad, pizza, or salad, pizza, or pizza. So let's look at what happens when we cons on pizza. To the empty list. We get back list pizza. What we really get back, though, is this. Pizza dot empty list. So we're consing the symbol pizza onto the empty list. What that's really returning is pizza dot empty list. And I can prove this to you because I can put a quote in front of that pair. And if I hit return, you'll see that it's printed as just the list pizza without a dot and without an empty list. So what's happening is if you have a pair whose cooter, or the rest of that pair, the second thing in the pair after the dot, happens to be the empty list, then that dot in the empty list disappears. That's not printed out. This is just to make it easier to read lists because lists are used so much. And so if I wanted to cons on, back to consing pizza on the empty list, if I want to cons on salad, so now I see the list salad pizza, but what that really is salad dotted to the dotted list, or dotted pair, pizza dot empty list. Put a quote in front of that, and we'll see that it looks like the list salad pizza. So when I'm taking, and this also helps explain, I think, what's happening when I'm taking the cars and the critters. So if I'm taking a car of this pair, whose car is salad, and his cooter is the pair pizza dot empty list, well, obviously the car is the first thing in the pair, so I can get back salad. And if I take the cooter, well, the rest of that pair, the thing after the dot, is pizza dot empty list. And so pizza, the list pizza, is the same as pizza dot empty list, which we've already seen. So if you think of it in terms of the cars and the critters, that allows you to build up structures that aren't what are called proper lists in Scheme. So a proper list is either the empty list, or it's a pair, something has a dot in it, whose cooter is itself a proper list. So it's a recursive definition. So something like 3.empty list is the proper list because it's a pair whose cooter is itself a proper list. And we can build that up inductively. So I could say 4 dot and grab that proper list and stick it inside. So 4.3.empty list is also a proper list because the innermost pair, its cooter is a proper list, and then so that makes it a proper list. And then 4 dot, that pair 3.empty list is itself a proper list. So the proper lists have this property that when they're printed out, you don't see any of the dots, and you don't see this empty list at the end. Okay, so just be aware. Most of the time, we're just going to be dealing with regular lists, but there are some times we'll be dealing with pairs, and we'll be constructing new pairs with cons, and we might construct some pairs that are not proper lists. And so you should just be aware that if you see something with a dot, that means just that we've conned something where the thing that we're that's in the cooter position and the second position of the cons just isn't a proper list. But there's nothing wrong with it. So at the end of the day, everything in memory in Scheme is really a pair. We don't have lists. Lists are just like a type of pair structure that we can build up. Okay, so that's cons to construct new pairs, or to cons onto the front of a list. We have list question mark. We have car to take the first element of a pair, cooter to take the rest of the pair or the rest of the list. We also have pair question mark. So if I cons 3 to 4, that's true. That is a cons pair. If I try to ask if 3 is a pair, it's going to say false. So that's false. Okay, so we've seen how to call a function. We've seen a little bit of arithmetic, and we've seen lists and pairs. And I know this is going fast. If you are familiar with Lisps before, then this probably isn't going too fast. But if you've never seen a Lisp before, this might be a little bit too much. And so I would recommend looking at the little schemer. I don't think the little schemer ever uses cons pairs that are improper, but it certainly uses lots of lists, and car and cooter and so forth. So little schemer is a really good reference for that. There's also How to Design Programs, which is a resource from the Racket folks, and that's available free online. That shows you how to use lists and so forth as well. All right, so let's try to do something a little fancier now that we know about pairs and lists. Let's also look quickly at, oh yeah, and I should just say, if you want to try to get a better handle on car and cooter and cons and all that, a really good exercise is just to build up some complicated lists. And so the lists, okay, sorry. Let me show you one more thing before we finish with lists that I had forgotten, which is we can have more complicated structures. So the lists that I was showing you before, which was like milkshake, I might call a flat list. So it's a list where each element is, in this case, a symbol. Okay, but you can also have lists where elements within the list are themselves lists. So, instead of having salad, we could have another list, which is salad and, I don't know, mustard. So now we have a list that itself contains a nested list. Okay, and we could also, instead of just a pizza, that could be a list containing pizza. And instead of milkshake, that could be some deeply nested list containing milkshake, for example. Or maybe I want to put, I don't know, I'll put a soda here. So now we have a much more complicated list structure. We can also do this with pairs if we want also. We can put pairs that have, that are improper lists with dots and all that stuff. But one good exercise to try to get good at understanding how car and coulter work is to try to just build up one of these lists. You can see I just kind of randomly typed in, I got a list. And then just play a little game, like maybe I want to extract mustard from this list. So how do I get the item mustard out of this list? So I could say, all right, well, I'll probably have to take the coulter first. All right. And now the first sub list contains mustard. So I need to take the car to get the first part of that list, the car, the coulter. And now I need to start going inside of that list. So take the coulter of that. So I have car of that list. And now I've gotten mustard. So it's the car of the coulter of the car of the coulter. And if I really want to, I could say it's the car of the coulter of the car of the coulter. List, and I should get back the same answer. So that's a good game you can play to make sure you understand how lists work and how car and coulter work. And you can also try to play the same game using cons to say, okay, here's some really complicated list. Let me make a bunch of calls to cons to build up that list. So if you want to practice with lists and pairs and so forth, I would recommend playing those games. That's what I used to do when I was first learning Scheme. I played a lot of those games, and just, if you spend half an hour playing with car and coulter and cons, you basically won't ever forget it again. So it's time worth spending. Okay, so now we know about lists, we know about nested lists, we know about pairs, all those sorts of things. So now let's get into something. Two more things to show you. And then we can have some real fun. So one thing is, how do you give a name to something? So we can define first to be the same as car. So define in Scheme just gives a name to some value. So the name we're giving is first, and the value is going to be car. And so car just happens to be a procedure in Scheme, or a function if you want to think of it that way. But now we've got a new function defined called first. And this function, you can see it also has the same behavior, car. This function now just behaves like car. So before we say car of ABC would give us A, and now I can call first. So define gives us a name. It gives us a way to give a name to some value, and we could say rest is the same as coulter. Back to this complicated thing I have, and I can replace the car here with first and the coulter with rest. It's the same behavior. Okay, so define is a way to give a name to some value. Another thing we need to know about is how to make some choices. So one way to make a choice in Scheme is if. We can make a decision. If true, then we return 3, otherwise we return 4. So an if expression has these parts. It has a test position, and if that test position evaluates to true, then we evaluate and return the value of the first sub-expression after the test. Otherwise, we evaluate and return the value of the second sub-expression after the test. So in this case, because hash t is true, we're going to get back 3. And sure enough, and if I say if false, we will get back 4. And I can obviously have more complicated tests, like if null the empty list, which is going to give us a true value, then I'll get back 3. And if null of 5 is false, I'll get back 4. And of course, I can put complicated expressions here, so I could add an addition. 3 plus 4, maybe a multiplication here. And if once I start getting into more complicated expressions, I might want to try reformatting my code to make it a little easier to read. Scheme doesn't care where you put new lines and things like that. as long as it's not in the middle of an identifier. So I can't put a new line between the U and the L. It's not going to make it happy. But otherwise, I can put parentheses almost anywhere. And in this case, we can clearly see what the test expression is and then these other two expressions. So if the test expression is true, we'll evaluate this expression and return its value. Otherwise, we'll evaluate this expression and return its value. And probably it's worth saying that in Scheme, any value that is not #f is considered true. So it's got a interesting definition of truth and falseness. So false is false. #f is false. Anything that evaluates to #f is false. But any other value is considered true. So 5 is actually considered a true value. So you'll notice that we evaluated +3, 4 and get back the answer 7. So any value other than #f is considered true. So like in cons pizza onto the empty list to get the list pizza, that's considered a true value in Scheme. All right, so we've seen how we can make a choice. We've learned about lists. We know how to make a function call. One other thing we need to know about is how to create a function. So let's see. Oh yeah, a couple questions here. So one question is, are Scheme lists linked lists? Yes, they are linked lists, singly linked lists of cons pairs. And another question is the empty list truthy or falsy in Scheme? Well, let's try and find out. The empty list, quote empty list, C, the 7, so that's considered true. So any value other than #f is considered true in Scheme. This is a decision, a design decision that you might debate, but that's how it works. So, and just to remember, you know, it doesn't mean that we have to type #f in this position. It just means that the expression has to evaluate. So if I ask if 5 is null, then that will evaluate to #f, and so this will be considered, this test will be considered to give us a false value. Okay, so it doesn't have to be the constant #f, but we have to have an expression that evaluates the #f there. Okay, all right, so the only other really missing piece we have is functions. And as soon as we have functions, then we can start writing interesting definitions. So let's do that. One of the key things in Scheme is something called Lambda. You may have seen from other languages. Here is an example of a simple Lambda expression. So my editor is set up so that when I type in Lambda, when I type in that A at the end, it gives me the Lambda symbol from Greek. That's just a thing that I've got enabled just to try to save space. But yeah, so you would type LAMBDA, and that would give you a Lambda. And so a list that begins with Lambda is going to be a Lambda expression. So if I evaluate a Lambda expression, I get back a procedure or a function, if you want to think of it that way. So this procedure is actually representing the identity function. This procedure takes one argument, x, and then just returns the value of x. So it doesn't change x at all, it just gives it the value back. So this is the identity function. Doesn't do anything to the value. X. So I can define this. Let's see, I'll define. And I can see if I type in identity now I've given it a name, I get back procedure identity. Okay, so I can apply the identity function now, procedure, to 5. Okay. And it gives me back 5. Or I could give it the list pizza salad. Pizza salad. So this procedure takes its argument x and returns it. So this first x is what's called the formal parameter. Okay, so this is just, we're giving a name to the argument that's passed into the procedure, and then we're going to return some value. In this case, we're just returning the value that is bound to that formal parameter, formal argument. Okay, so that's a very simple example. We could have a more complicated function. That's something a little more complicated. So one thing we could do is, instead of just returning x, maybe we multiply x by itself. In fact, I might want to give a name to that function. Instead of calling that identity, maybe I'll call it square. So now I've got a function called square, like 3, and I get back 9, or 5 to 4, and I get back 16. So this is a function that takes a number x and then multiplies x by itself. Now you notice I said it takes a number x, but I didn't specify x had to be a number. In fact, I could pass in anything I want. I could pass in, quote, pizza, and in that case, I get an error. Exception in star, or multiplication, pizza is not a number. So it's trying to multiply pizza, the symbol pizza, by the symbol pizza, and it doesn't know how to do that. Multiplication is only going to work on numbers. So scheme is a dynamically typed language. It will give me a type error at runtime if my types are incorrect, but it's not going to stop me from, you know, defining square and then calling it or something like that on a non-number. It's going to actually try to execute that. So that's the difference between Scheme and Java or ML or Haskell or those languages that are where the type system would disallow my typing that or entering that. Okay, so I can square numbers, great. Now, if you notice, what I did was I defined a function called square, and then I applied square to the number, to its argument. So I did 2 steps. So we try it on 5, square 5. But I did, these 2 steps. So I defined square up here, and then I applied the variable square to 5. It's actually in 1 step. I don't actually have to give the procedure a name. What I could do is just copy the procedure and enter it right here. So now notice I don't have a name for this function. I'm not calling it square anymore. I just have the Lambda expression by itself, the raw Lambda expression. And I'm applying the value of that Lambda expression to 5. And it turns out that works exactly the same way. So I don't have to give a name to Lambda expressions in order to use them. This is creating what people call an anonymous function. You ever heard that term? So it's a function that doesn't have a name, but I can apply it without any problem. Okay, question. Is it idiomatic or possible in Scheme to redefine Scheme to turn times pizza pizza into, to a concatenation or something like that? Okay, so the question is, if we are maybe unhappy that our square function doesn't work well on pizza, maybe we want to redefine somehow. Maybe we want to redefine times. So now I can do a different operation when it's being passed a symbol instead of a number. And we can do that in Scheme. In fact, one of the good things and bad things about Scheme, depending on how you look at it, is I can redefine almost anything in Scheme. I can redefine times so that it no longer multiplies 2 numbers. In fact, maybe I can redefine, maybe I'll redefine times to be plus. Okay, so now times will do addition. So let me go back to this example. And now instead of squaring 5, I'm adding 5 to itself. Okay, so now I've just clobbered definition of times. I just redefined it to do something entirely different. And I could create a function here that takes some number n or takes some value x, and maybe it just returns x. Maybe I've made now it's the identity function. I could do all sorts of things, or I could make it be a function that takes 2 arguments and returns the first of those. So if I do that, then I could pass in pizza. And instead of trying to multiply pizza by pizza, it's just going to return pizza as this first argument. So there are all sorts of games I could play. I could try to make it concatenate itself. I could turn the symbol into a string. If you want me to do that, I can. So I can do something like there's this thing called symbol to string on X, and then so I'll actually get a string back, the string pizza, which you can notice has double quotes instead of a single quote in front of it. And then I could do something like string append that against Y. So turn X and Y from strings into symbols, so from symbols into strings, and then string append them. Let me try that. Yeah, and so in this case, I get back pizza, pizza. So I could do those sorts of games. Now, I could also try to check to see what type I got. I could say, all right, you know, X is a number, then maybe I multiply X by Y. And otherwise, I'm going to do this string stuff, right? You know, do something like that and define times to be a function that now can handle pizza, but can also handle, you know, oh, all right, I screwed something up there. What'd I do? Oh, okay, this is funny. Yeah, so I wrote it. Yes, I made it recursive here. So what I would have to do is call the built-in function. Maybe I make it do an addition instead, but I would have to call in the built-in definition of times, because you can see I'm actually redefining times here. So I'm defining times, and now I'm calling times. So this is a recursive definition. Then I'll get into an infinite loop if I'm not careful. So what I would really want to do is call this built-in scheme, built-in schemes definition of times, which I can do. So in Shea scheme, there's a special syntax that lets me get the built-in definition of times, which isn't something I can overwrite. So I could do things like that, or I can make it say number instead. So yeah, there it to itself. Otherwise, I can do the pizza, and I'm concatenating, turning the symbols into strings and concatenating them and stuff like that. So I could play all sorts of games here. I mean, it seems extremely flexible. Whether or not it's a good idea, that's a matter of taste and programming practice. Yes, I accidentally gave a first recursive definition. All right, so I'm going to restart because I may have covered a little too much state. But the main point is that we have the definition. We have the ability now to define functions, okay, and to apply those functions. We have the ability to give something a name using define. We have lists. We can make choices with if. So now we have enough pieces to start writing recursive definitions over lists, and this is when we start, you know, being able to do really schemely things or Lispy things. So let's write a simple function that will, well, let's just write length. Length's a good one. So we already saw what length does. So length of ABC is going to give us back 3. Length of the empty, whoops, got to finger that. Yeah, so length of ABC is 3. Length of the empty 0, right? And you know, so let's just define length as a function. So we want to call. So we'll, you know, we can clobber length if we want to. We can rebind the name to our own definition. Now let's call it my length, just so we can still have the old length around to compare its behavior. So we're going to define a function called my length. All right, and my length is going to take. We're going to make my length the lambda. Hold on 1 second here. I think my Emacs got in some weird state. Okay, so we're going to find a function called mylength. And so we have to decide, first of all, how many arguments is mylength going to take. So mylength is going to take a single list. So I might call that list ls as a convention. And now we have to make a decision about what to do. What is mylength going to do? What value we return? So mylength is just going to behave like length, and it's going to return a number that tells us how many, basically how many cons pairs are inside of ls. So we have to decide, well, what should the length of ls be? Well, it's going to depend on whether or not ls is the empty list. Because if ls is the empty list, then we know that the length of the empty list should be 0. So as we're defining this function, we can say, all right, decision. If ls is the by making the small test, then we're going to return 0. Else, I don't know, we'll return 5. Who knows? Okay, so we're not sure what to write there yet, but we already can now start testing it. So we can see mylength of the empty list. Sure enough, we get back 0 on the empty list. Okay, so we're just making a simple decision to check whether or not the list is empty, and if so, return 0. Otherwise, we're going to do something else we haven't decided yet. So you can see the parts that we're using. We're using define to give a name, mylength, to a value, which is the result of this lambda. So this lambda is going to create a procedure. You can see that the name mylength, we're allowed to have hyphens in the names of scheme functions, which is nice. And we're using an if to make a decision. We're using null to check to see if a list is the empty list. And we're returning a value in either case. So this if is really an expression, not it's not an if statement. It's an if expression because it's always going to return a value, and we're interested in the value it returns, not in some additional behavior like printing something out or streaming to Netflix or whatever it is. Okay, so we just want to know what the value of this if expression is. Okay, so we've already written a fair bit of our function. We just have to finish it up. And the finishing up part is the interesting part here. We have to decide what's going to go here. Well, I guess where it gets tricky is that the length of the list could be anything, right? So, we know the list isn't empty, but the list could have 1,000,000 elements in it, or 1,000, or 1,000,000,000, or 1,000,000,000, or whatever. Could have 137 elements, or 42 elements, or whatever. So, how do we decide what to do? Well, what we're going to do is make use of one of the most powerful ideas in computer science and computing, which is recursion. What we're going to do is we're going to call mylength on a smaller list. That's the basic idea. And let mylength do its thing on the smaller list. And we're not going to worry about how it does that. It's just the magic of recursion. It's just going to work. And then we're going to do some work with the result we get back. So basically, the key idea here is that we're going to have to make a call to mylength. And we know mylength takes a list, ls. We need to make sure that the list gets smaller, because otherwise we'll get into another one of these infinite loops where, if we call it with the list ABC and we never make it smaller, if I just call it with ls again, then this will just keep looping forever. We'll just keep calling my list of ABC forever. In fact, I can show you that. So if we call my list ABC, my length doesn't come back. And in fact, I can show you it. Okay. Now if I try it, you can see that JScheme prints out a whole bunch of calls to mylength, and they all have the same list in their place. So we don't want to do that. We don't want to just keep passing in the same list over and over again. We want to make it smaller. So The way we make it smaller is by taking the rest of the list, by taking the quarter of the list. That means the list will be smaller. We're always quartering down the list, throwing away the first element. That way we know our list is going to get smaller. Okay, so this will now terminate, so I can call my length of ABC. And now terminates, it doesn't go in an infinite loop anymore, but it's not giving us the right answer. Okay, so even though we're making the correct recursive call, we need to do some additional work in addition to the recursive call in order to get the right answer back. And so if we think about it, my length of list A should actually be 1. If we just call length of list A, that would give us 1. So we're off here. So we were forgetting to do something. And what are we forgetting to do? Well, we're forgetting to add to the number. We're not adding anything. So what we need to do is, in that recursive case, we need to add 1. So I can add 1 to the result of the call to my length. Now if I do it, if I do it on ABC, I get back 3 as I expected. So what I need to do is make sure that in addition to making the recursive call, I do some operation outside of the recursive call that will give me the expected output. It's not enough to have the correct recursive call. So that's my length, and that's the first example we've seen of recursion over lists. And let's try doing something else. Let's try doing, how about we try doing count 5s? Okay, so count 5s is going to work like this. We'll give it a list, and it'll be a list of numbers. And what it's supposed to return is the number of 5s that appear in that list. So here we got a 5, here we have a 5, here we have 2 5s. So that should give us back 4. Okay. So we're just going to recurse down this list, count up how many 5s we have. All right. So let's go ahead and define it. Define 5s. Argument. And we're going to see if the list is empty, how many 5s should we return in that case? Well, 0. Now what's going to happen? Well, now we know the list isn't empty, so it has to have a first element, which is a car, the car of the list. And so now what we have to do is make a decision. We have to make a decision based on the value of that car, whether or not the car is 5 or not. So what we can do is have another if that's nested. So we can ask if the car is 5. So this equal sign allows us to do a numerical equality comparison. So if the car of the list is 5, if the first element of the list is 5, now what are we going to do? We're going to add 1, just like we did before, to some value. Well, what that value is, the value is whatever count 5s is on the rest of the list. So once again, we're going to have a recursion. Else, one more case here, else, in this case, well, the first element isn't 5, it's something else, in which case we're not going to add 1 to it, but we still need to count up the rest of the 5s in the remaining list, the remaining part of the list. So we're going to still do a recursive call, it's just we're not going to add 1 to the recursion. Let's see if this works now. I get back 4. And sure enough, we get 4. So another simple example of recursion. Now the thing that's a little annoying is, now I have these nested ifs, and that takes up a lot of space. I'm moving off to the right of my screen and so forth. And this is so common in Scheme that you would write these nested ifs in recursive definitions that there's another way to make a choice, and it's called cond. Cond. Cond stands for conditional. It's short for conditional. So cond allows us to make multiple choices at the same time with a nicer syntax. So basically, the way cond works, cond allows you to have one or more clauses And for each clause, you get to have a test, and then you have a value to return if the test. Here's our first test, our first clause. And here's the test for the second clause. And here's what we do if that test returns true. We'll return that. Line. And then if the first two clauses, if neither of those is a true value, then we're going to have a special clause that has a special test called else. It's always going to happen if we reach it. So what's going to happen is we'll try the clauses from top to bottom. We'll try the test in the first clause, and if that succeeds, we'll return the value that happens after the test. Otherwise, we'll move down to the next clause and try its test. Now, this one thing you might see in some implementations or some books or whatever, you might see people use square parentheses instead of round parentheses. There's nothing special about square parentheses. It's just another type of parens that you can use in some implementations to read the clauses, because now the test really sticks out and the clause sticks out. So the clauses begin with squares and end with square parens, and the rest of it inside we'll just use the round parens. So it's just a way to visually set aside the clauses a little better. Okay, so this has the same behavior and same definition as our count fives before, but it's shorter and it's easier to read. So cond is actually the way that we're going to write our programs. Either that or we're going to use a pattern matcher in general. Okay, so I feel like that's a pretty fast, but very incomplete, but enough of a intro to get started. And so now I guess I'd like to open up to questions, and also try to together write a couple of definitions that are recursive. And Sean asks, does +1, 2 have the same behavior as +1? Okay, I see. Okay, so you've got a question about the square parens. So you want to know if +1, 2 behaves the same as +1, 2, and they do. It doesn't mean anything in Scheme, as long as the parens are matched. What you're not allowed to do is you're not allowed to do something like this. You're not allowed to have squares and rounds that are mismatched. Okay, but otherwise it's exactly the same. There are some Lisps or some implementations where the squares might syntactically mean something different than the round parens, but not in Scheme. And I should also point out that not every version of Scheme, not every implementation of Scheme allows the square parens. The Scheme have pattern matching. It doesn't have it built in, but you can easily add pattern matching because you have macros in Scheme. And so we'll take a look at that at some point. Racket has pattern matching built in. Racket's the battery included. Daniel, okay. Daniel points out in closure, the square +1, 2 would give you a literal vector. Okay, yeah. So in closure, there is a difference between round and squares for this. Okay, so this is a little bit of a difference between closure and Scheme. In Scheme, we're just purely using it for a convention. And if you look at, say, the little schemer or the reason schemer, we always use rounds just to try to avoid any of those issues. But sometimes you will see code that uses the squares, and just understand that's a convention. That's nothing important. That's just to make it a little more readable. Okay. Right. Raja asks, do all conditionals begin with an implicit begin? So all the con clauses. Okay, so I haven't talked about begin, but I can show you it. So Scheme has something called begin, and I can put in several expressions in here inside the begin, and only the last one, only the last one's value will be returned. However, begin can be useful because I might want to print out some information or do some other, it's called a side effect. I could say hello. And then here. And maybe I put a new line. And so what happens when I evaluate this begin expression is each sub-expression in turn gets evaluated. So display will print something out to wherever the output is for this version of scheme. In this case, it's the Emacs buffer, but it could be to a different window or whatever. So I'm going to display the string hello, comma, with a space, and then I'll display world with an exclamation point, and then I'll generate a new line, and then I'll also return the value 5. So it's important to tell, and it's hard to see in this window, but it's important to understand that the value of this begin expression is 5. It has nothing to do with this output that's being printed. So I could take that begin expression and I could add the begin expression to 6. And that's perfectly legal, and I'll get back 11. But you'll see that it also printed out hello world. Okay, so begin is a way in Scheme to have these effects like printing output or reading things in, and then still return a value at the end. Okay, so the question is, does Cond have an implicit begin? So let's try. So let's go back. Let's just try writing a Cond expression. Cond doesn't have to be inside of a function or anything like that. I can write inside of a Lambda. So I could say, if empty list is null, return 3, else return 4. Okay. I'm sure 3. So I could try, though, doing a begin. Or sorry, yeah, so let me try an explicit begin. I could say display, and then 3. Displays foo, and then I didn't put a new line this time, and then I get back 3. So now the question is if I remove the display, or sorry, the explicit begin, and just have display in 3, what happens? He has the same behavior, so it's basically a begin. It's an implicit begin. Good question. Is there a way to refer to the previous definition, like so? Define plus lambda previous. Okay, so let's try this. So you want to know if we can write this, something like that. Let me make sure I understand. Okay, I think I understand what you're. So what you want to know is sort of, can we save a function or save a definition so that we can redefine it without causing trouble? Is that the idea? So before we redefined times, right? So maybe we want to keep times. So let's try doing something like this. So let's say define old times the multiplication function, old times, and so I can call old times 3, 4. Okay, and that's the same as times 3, 4. Okay, so now let me define this to be plus. Okay, so now I'm redefining star to be plus. So now if I write star 3, 4, we're going to add them instead of multiplying them. So I get 7. And what if I do old times still? I still have my multiplication around. So I could do things like that. I can temporarily save things. There are more sophisticated ways in Scheme. There are like libraries, and there are also notions. Shea Scheme supports something like modules. So there are ways to control what's called the namespace, where things are defined, where variables have scope that allows us to play those sorts of games. Okay, those are good questions. All right, so let's try just defining a couple more list related functions. Let's how about since I clobbered some things, let me just restart. How about how about we do append? That's an old favorite. Append, or you might know this as concat. So we're gonna take two lists, and we're going to concatenate the contents of this list together. So list ABC to list DE will give us ABCDE. Okay. So let's define append. So can anyone help me out? What am I going to type first? Define my append. That's a good idea. Okay. So all right. And of course, I could call it append also, although I'll clobber the built-in append. So, it's up to me. All right. So what would be the next thing to write? Okay. So two args. So in particular, I want a lambda expression that arguments. So these are going to be two lists. So I could be like L1 or L2 or L and S for the two lists. That's what I tend to do. Okay. And now I'm going to have an if. Okay. All right. Because I have to make a decision. That's fine. All right. So what's the first decision I have to make? Well, so here's a general rule. That's right. Roger's got it right. So whenever I'm dealing with lists, almost always the first test is to see if the list is null. So we have to make a decision to see if a list is empty. Because if a list is empty, then it's not safe to find the first element of the list or the second or the rest of the list because it's not defined. So what we're going to ask is if one of the lists is empty or null. And we have to decide now, do we ask that question about the first list or the second list? Well, in this case, I'll just give you a hint, and I'll say it's probably better to do it on the first list, okay? So we're going to ask to see if the first list is empty. And if the first list is empty, then what should we return? Well, I don't know, maybe we got stuck, we're not sure, but we have append here, so we can try it out on append. So we can say append of the empty list to list DE should give us back DE. Okay, so now we know we should actually return the second list. The second list should be there. So in that case, if L is empty, the first argument is empty, then we're going to return the second list. Okay, great. Now, and by the way, this is called the base case of the recursion. And then we have the recursive case. All right, so in the base case, we're just going to return S. And now we have the recursive case. There are no more tests to be made. We have to go ahead and process the rest of the list. So what are we going to do? Well, the way I think about it and the way Dan taught me is we know we're going to make a recursive call. So let's go ahead and write that first. Okay, the recursion, we know we're going to have to write that first. So we can call my append. How many arguments does my append take? Well, we can look up here at our lambda. We know it takes two arguments, L and S. Okay. One of those arguments at least should get smaller because otherwise we'll get in an infinite loop if we just pass the arguments in as they were before. So we need to get closer to the base case. And the base case test is null of L. So in other words, the list L eventually has to become empty so that we'll terminate, or our program will eventually stop running. So what that means is that L has to get smaller. We have to make L smaller in the recursion. So we can do that taking the quarter of L. Taking the quarter of L in the recursion will make it smaller. What about S? S is the second argument. Well, we didn't actually ask any questions about S in the test for our base case. So most of the time, what that means is that S isn't going to change. We will leave S unchanged in the recursion. Okay. Now, now we're going to play a very special game. This is a game that Dan taught me. So we have an incomplete or incorrect definition of my append. So let's just try the incorrect definition of my append on kind of what we were trying to do before. So here is our example. If we remember, append ABCDE should give us ABCDE. If I do my append with our current definition, which makes a recursive call but doesn't do anything else, we'll see we only get back DE. We only get back this list, S. So something's not quite right. But here is a magic way to think about it. Let's, instead of calling my append, let's call the built-in append. Okay, let's call scheme's built-in append, which is already written for us. And it's a correct definition of append. So we're gonna, instead of making a recursive call to my append, we're gonna call append and see what happens. See if we get the right answer. So remember, append ABCDE gives us ABCDE. And now we're gonna call my append ABCDE, and we get back BCDE. So even when we called the built-in definition of my append, we didn't get the right answer. We're missing the A on the front. And if we wanted the right definition, if we wanted the right answer, what we'd have to do is something like cons A onto this list BCDE. We have to add A to the beginning of that list. What this is telling us is that we need to add a call to cons outside of our recursive call. And we need to make sure that A somehow gets on there. Well, what was A? A happened to be the car of the first list, or L. So there's A. So what this is telling us is that the car, or the first element of the first list, needs to be consed on or added to the beginning of the list we get back from calling append. Try it again. And now we get back the right definition. Okay. And now, here's the amazing part of the trick, is that remember, we were calling append. We were calling the built-in definition and scheme. But now we can make the realization that actually, we don't need to call the built-in append. We can just call our append recursively. And sure enough, it works. And the amazing thing is this type of thinking works even if append were not defined for us already. We can play make-believe. We can say, oh, well, maybe Dan has written a version of append, so we'll call Dan's append first. Or whoever. Maybe someone else has written a version of append. And so we can assume that we have some correct definition of append, and then we can play computer and think, okay, well, if we had the correct definition of append that worked the way we expected it to, are we still missing something that has to happen outside of the recursion? And if so, we'll need to add that. So this is a way of playing make-believe, where we pretend that we have access to the correct definition for the recursion, and then we try to figure out what's missing on the outside of the recursion in order to get the right answer. And that's a very powerful technique, and I use it all the time. So now we actually have a correct definition of my append. Now we could also rewrite this using cond instead of if. Get used to our cond. So we can say cond. Clause here. And we've got an else clause. A little bit. Right, and that my append works just fine. So that's a nice definition of my append. All right, so let's try another example. How about, okay, so let's try an example. Okay, so how about we have a function like, I don't know, combine. Takes A, B, C, D, and it takes 1, 2, 3, 4. And what it produces is 1, B2, C3, E4. Okay, so that's the function we want to define as this combined function. So at that tests, we could also write another test with the empty list. So the two lists were empty. We're going to assume that the lists are always the same length. Empty list to the empty list gives it back the empty list. Okay. All right. So those are two examples. So let's go ahead. It has to take two lists, just like a. Perhaps interleave would be more descriptive. Okay, fair enough. All right, we're going to interleave these two lists, the elements of these two lists. Okay, so we're going to have a cond here. And we have clauses here. I use the square brackets. So the first thing to point out is that we can already define a fair amount of interleave without having to do any real thinking. So we know that we have to have define because we're defining a function. You have to give it a name, so we have to have it defined. We're calling it interleave. We can tell that from the calls. We are going to have to create a function with Lambda. The Lambda is how we create functions. And we know from these example calls that we're going to take two arguments, which are lists. So call them L and S. So we have two arguments coming in. And this is going to obviously be a recursive definition because the lists could be of different lengths. So we're going to have to recur so we can make decisions and so forth. So it's going to be a recursive definition. And therefore, we're going to have to make a choice. We're going to have an if or a cond. We'll use cond by default. So we know we have at least two clauses because we're going to have a base case and a recursive case at least. We might have more than one base case, something like that. We might even have more than one recursive case, but we know I'll have at least two clauses. And furthermore, we know we're going to be making a call to null to see if a list is empty. And usually it's on the first argument. So at this point, we actually already have a whole lot of structure. So we didn't really have to think about any of this because we're recurring on lists and we know we have to eventually get to the empty list. We're going to have call to null at least on one of those two, maybe on both. In this case, we actually, because they're the same length, we actually could combine. We could say if L is null and S is null, I'd write like this. This could be a test. So and allows us to do Boolean operation where and of null L1 and null null L and null S is going to be true only if L and S are both null. But if we just make the assumption lists are always the same length, could write it this way as well. So I can be very very lazy in a sense in terms of thinking and still have a fair amount of the structure. So I can at least write that down without having to really think at all. Okay. Let's see, a couple of comments here. Base case returns the empty list. Yep. Now that we can tell just from looking at the first test, right? So we really aren't having to think even there. So we've already done a lot of the work without having to do any real thinking. Usually the first, because cons makes it easier to build lists by adding new elements to the front. It is usually the case that the first element is where you're going to take the first list, the first argument to Lambda is going to be the one where you're taking the null test of. Why is that usually the case? I think that's maybe more convention or it's like, you're usually going to be recurring on at least one element, one argument. And I think in Scheme, it's just common to put the argument you're going to recur on first, because that's sort of the most important the most important in a recursive definition is probably going to come first. So because you're recurring on it. So, but that's just convention. It's, you know, you could mix them around any way you want. So that's not a hard and fast rule. You know, so if you really want to be safe about it, we could use this and thing. Well, I think, you know, do it that way as well. All right. Shouldn't that be an or? Well, if we assume that L and S always are going to be the same length, then it's not, doesn't need to be an or. You know, that's exactly why I don't need, I can just put the one test, right? I could just do it on S as well. So as long as we're making the side condition, which is L and S always have to be the same length, it doesn't matter which one I ask the question of. It's going to be the same. Okay. So now the question is, do I have any more decisions to be made? Do I have to you know, look at the first element of this list, like A? Do I care if it's an A versus a B? Do I care if it's a 1 versus a 2? Any of those sorts of things? In this case, no, I don't actually care what the value is. So I don't have any more base cases or anything like that, or any other recursive cases. I'm just going to have one recursive case. So I know that's my second con clause is it, and I'm just going to have an else as my test. So this is the only thing we really have to do is the recursion. Yes, but in the case of unequal list, or would give you early termination rather than the car coulder of the empty list. Yeah, so what Daniel's pointing out is that we could define this so that if we used or, you know, we could still give a meaning to this even if the lists were not the same length. You know, so we could decide that if one list is shorter than the other, maybe we just put on the remaining elements of that list, and we absolutely could do that. So let's do it first using this way where we assume the lists are the same length, and then we can try modifying it to handle when one list might be shorter. Okay, so this really just comes down to what we want the function to do, and which you know, sort of our contract for the function. Okay, so let's play our game. Our game is we're going to make a recursive call. We know we have to make a recursive call, so we go ahead and do that. But we're not going to call our interleave. What we're actually going to do is pretend instead of making a recursive call, we're going to call Dan's interleave. So Dan, schemer, so he knows about recursion. So we're going to trust that his code is correct. Okay, so we're going to call Dan's interleave and assume that that's going to give us the right behavior. And now we know it has to take 2 arguments because it's going to have the same interface as ours. So it's going to take an L and an S. And we've made this assumption that L and S have to be the same length. So that's really the same as doing an and here or an or. I'll start out with the and version for now, and then we'll change it to or. So if we think of it as this way, as the and of the nulls, then we're actually asking questions of both the tests, of both lists, L and S. So really, what should be happening is we have to get L and S to be smaller in the recursion. So we're going to take the quarters of both of those, okay, to make those smaller in the recursion so we don't get into an infinite loop. All right. So now we sit here and we play make-believe for a second, and or play computer, and we ask ourselves, well, what would happen if we were to call, say this call to interleave with the definition we have below? Okay, so play computer here. So interleave A, B, C, D to 1, 2, 3, 4. So what does that mean? So it means that we start off with L, the variable L, first variable in Lambda is equal to ABC. And LS is going to start off as 1, 2, 3, 4. We're going to make a choice within our con. We're going to ask, is L null? No, L is not the empty list. Okay, and S isn't the empty list either, for that matter. So we're not going to run the base case. Instead, we're going to go to the else case. And now we're going to call Dan's version of Interleave on the quitter of L and the quitter of S. Okay, so let's think about what those are. So the quitter of L is going to be the rest of L, which is B, C, D. And the quitter of S will be the rest of S, which is going to be 2, 3, 4. Okay. All right, so what this means is we're going to end up calling Dan's Interleave on the list BCD and the list 2, 3, 4. And remember, we're playing this game where we assume that Dan's version of Interleave is written correctly. So it should behave the way we would expect the correct definition to work. So by our understanding of how this function should work, we should be getting back B2, C3, D4. Okay. And we compare that answer from calling Dan's Interleave to what we expect to get, which is up here. And we notice that we're missing the A and the 1. Those are just missing from the answer entirely. So if that's the case, that means that we're missing the first element of L and the second element, or in the first element of S from the answer. So really the car of L and the car of S need to be added. So we're going to cons on car of L and cons on the car of S. Shouldn't say and then because this happened inside out order. So this recursive call, or this call to Dan's Interleave happens first. Then we cons on the car of S, and then we cons on the car of L. So if we add the car of S and then the car of L to the result of Dan's Interleave, we should get the right answer. And this is where the magic comes in. We realize that we actually were writing the correct definition of interleave all the time through the magic of recursion. So we can go ahead and not call Dan's interleave. We can just call our own interleave. So let's try calling interleave. And sure enough, we get the answer we expected. And the other thing I'd like to point out is, so just like when you're dealing with lists, you're almost certainly going to ask a null question mark about, or null test about at least one of the lists. And your base case may very well involve the empty list. Also, when dealing with lists, in addition to the recursive call, you're very likely to be doing consing, to call cons or possibly append to either add something onto the list you get back or to append to lists. So it's very common to be consing something on to the answer you get back from the recursion. So that's a pattern you'll also see a whole lot. All right, so comments. Okay, does Scheme support doc strings distinct from comments? No. So if you look at languages like Python, and I believe Clojure supports this, they have something called doc strings where you can put in the definition of the function some special comments that you can either ask about the function in the REPL and it'll give you some information, or it'll generate documentation that's really nice that tells you additional things like the lengths of L and S have to be the same. Scheme doesn't have doc strings, so you would have to put that in the comments. You could explicitly check for this to check to see L and S are the same length. You could have something called a contract, so Racket supports this mechanism called contracts where you could throw an exception basically if L and S are not the same length. But at least Scheme doesn't support doc strings. Now I think Racket does support probably something equivalent to doc strings, but I haven't used that. Maybe someone can tell me about that. Okay, so going back to Daniel's point. So Daniel's point is that instead of using the and making this assumption and having to write the docstring or whatever, that the two lists are the same, maybe instead we have an or, okay? And instead, maybe we change the meaning of the program, extend the meaning so that we have some behavior when the lists are not the same length. Okay, so that sounds like a promising thing. So let's think about what we might want to happen if the lists are of different lengths. So we might say something like, well, maybe the first list is shorter. Maybe what we want to happen is this will be A1, B2, and then maybe 3, 4, or something like that. Maybe we just put on the rest of the elements. Okay, so that seems like that could be reasonable behavior. That might be what Daniel has in mind. And then the other case might be when the second list is shorter. So let's see. If the second list were shorter, maybe you have something like that. So we have A1, B2, and then CD. Okay. So is that in mind? Yeah. So is that right, Daniel? Unequal lists will interleave up to the length of the shortest. Yeah. Okay. So I think I've got what you have in mind. So let's look at our definition. So we could change this test to an or. So our base case is going to change a little bit. So if either list, if we cutter down it and run out of elements, we'd run out of elements in this first list there, then we would still have 3, 4 left over. And in this case, we would run out of elements in the second list, and we would still have CD left over. And we notice that 3, 4, and CD end up at the end. So what we could do here, basically what we want to say is that if L is null, then we want to return S. And if S is null, we want to return L. So probably the way I would do that is I'd write this as two separate clauses. And let's see if that gives us the behavior we want. Okay. Okay, I see. All right, so I misunderstood. So I thought Daniel wanted to do this thing where it's not interleaving at the end, but actually Daniel just wants to cut it off if one ends up not being okay. So do this. So Daniel's semantics are a little different. So he says when you run out of elements, then you should stop interleaving. So in other words, we would get back this answer. Is that right? So yeah, okay. All right, so let's try that semantics. All right, so this is where we're going to go back to our or, I guess. Pauses. I see. So in that case, then we just return the empty list. So let's see if this works. Okay, and then we had the other test where the first list was longer. We get A1, B2 back in. Okay, great. All right, so we have 3 different versions of interleave, and you can decide what you want. You can decide, do you want to cut it off prematurely? Do you want to insist that the list be the same length? Do you want to just fill in the rest of the elements if one of the lists runs out? Okay, and that's a design or taste or may depend on what you're trying to do decision, but you can define all of those very easily. And notice that we only had to change the base case. It's trivial change the base case to make those, get all 3 of those semantics. Yeah, so Daniel points out that with the first definition I have of interleave, I was just if you just change the and to the or, you get this behavior where it will automatically stop if one list runs out. So, and this still is making still asking questions about both L and S. So we still need to take cooters in both cases. So that reasoning holds. Good. Okay. So we've been going on for a while, and I feel like this is probably plenty of material. And for many people here, I'm sure this is old hat, but we kind of have to do this before we can get into the more sophisticated things. And for people coming from maybe like a closure background who are not familiar with Scheme, maybe you saw a couple things that you hadn't seen before. So so let's go ahead and end it here, stop the broadcast, and we'll pick up next time. And if anyone wants to hang out and talk and ask questions or whatever, then we can do that. All right, thanks. See you next time.